Hi everybody, welcome. This is going to be a pretty quick one. We're going to talk today about wave phases, and we're going to look at wave phases in two ways. The first is as a comparison of the position of 2 points on a single wave. So here I have this wave. We see it starts at 0, goes up, down, So we have half a wave, half a wave, half a wave, or we can say 1.5 wavelengths here. 1.5. Great. We also have a few crests just to cycle back to the properties of waves. B and G are both crests. D is a trough. A, C, E, and I don't have a point labeled here, but those are all intersects with the x-axis. And this is a physical wave, right? It's not a model of SHM, so we would have position versus position as opposed to position versus time. So when we talk about phases, we're talking about taking a measurement of angle between points in order to express how far away those points are from each other. So if we look at this as a sine curve, which it is, we know that from A to B to C to D to E, we have one full wave, right? And one full wave, one lambda, is equal to, we can say, 360 degrees, right? Or we can say is equal to 2 pi radians. Those all work just fine. So I can then say that A and E are 360 degrees away from each other. When I talk about phases, I would say that A and E are out of phase by 360 degrees, which we can also then say is called in phase, okay? So A and E, okay, are what we call in phase, okay? When I say that, I mean they are 360 degrees from each other. That's what that word in phase means here. Now, A and E are in phase, but A and C are not in phase. I can say that A and C are half a wavelength apart. B and D are half a wavelength apart. C and E are half a wavelength apart. So what I can say for all three of these is these are, well, what is half a wavelength? That's 180 degrees. So they are out of phase 180 degrees. Okay, so these two being half a wavelength apart are out of phase by 180 degrees. I can also write this as 2 pi out of in phase, or I can write this as pi out of phase. Another possibility is A and B. And I'm running out of space here, so I'm just going to keep the next one short. I can say A and B, or let's say C and D. Well, these are out of phase by, well, it's a quarter of a wavelength, so that's going to be 90 degrees, or pi over 2. So when we're comparing points on a wave, we can talk about those waves being in or out of phase. In phase being 360 degrees, or 2 pi, or one full wavelength. All those things work. Or if they're out of phase, we can talk about how many degrees they're out of phase, knowing that when we deal with a sine or a cosine curve, we can refer to the amount of degrees as where along that sine curve we are. F and G is a little different, right? E to G we know is 90 degrees. F is halfway between those two, so that's going to be 45 degrees, or pi over 4, out of phase. So that's when we're comparing points on a wave, but we very well may want to, let me get rid of that right there, make a comparison of the position of two waves. And if we want to make a comparison of the position of two waves, we're again going to talk about phase. Here I have two of them, right? I have A, which is blue, and I have B here, which is red. Just looking at these waves, we can say a few things about the properties of these waves. I can say that the frequency of A is equal to the frequency of, oh no, excuse me, whoops, I'm thinking of SHM. I can say that the wavelength of A is equal to the wavelength of B. I can't necessarily say that the frequency is the same because, again, this axis is not time, this axis is displacement. So the wavelengths are the same. I can also say that the amplitude of A is less than the amplitude of B, right? A is shorter than B is. They both have the same number of troughs, they both have the same number of crests. What I can also say, but that wasn't covered in the last lesson, is that the energy possessed by A is less than the energy possessed by B. And that is for the same, that is because the amplitudes are different. A greater amplitude will correspond with a greater energy. One way to think about this is when you think of waves, we often think of ocean waves. A ocean with much higher waves is going to have more energy, right? A wave coming at the beach that's much, much taller is going to crash, make more noise, and spread the water out further, possess more energy, had more energy because that amplitude was higher. But going back to this idea of phase, we want to make our comparison of phases. Well, A and B are right over each other, right? The crests match up, the troughs match up, they intersect at the same points. So I say here that A and B are in phase. Or in other words, they're 0 degrees out of phase. Right? They're 0 degrees out of phase. They're not shifted with respect to one another. I could also say, like I did with when we were comparing points, that they're 360 degrees out of phase, right? Or they're double that. Or I could say 6 pi out of phase. When it comes to a wave, because we view them as continuous, we really don't care that much. It's the same thing as 0 degrees out of phase. This is, again, 2 waves that are in phase with one another. Now, because they're in phase, they'll interact with each other in an interesting way that we'll talk about more next week. That's as opposed to something like this, right? Where I again have A and I again have B, but they're kind of shifted now. The crest of A lines up with the trough of B. The crest of B lines up with the trough of A. The crest of A lines up with the trough of B, and then the intercepts are the same at all of these points. So this wave, I can go ahead and say is out of phase by, but let's see, if they're the same wavelength, these are the same waves as before, and each crest lines up with each trough, that means that one of them is shifted by 1 over 2 lambda. So I could say it's out by 1 over 2 lambda. A wavelength is shifted. Or, since we want to talk about angles here, I can say 180 degrees. Or I can say pi radians. This is out of phase by 180 degrees or pi radians. This is sometimes referred to as completely out of phase. All right? So again, because it's completely out of phase or shifted by 180 degrees, something interesting will happen, and we'll explore that more next week. Something slightly more complicated can be shown with this one here. This one here, where we notice the crests don't line up with the crests, the troughs don't line up with the troughs for waves A and C here. I don't know if you can see it, but A is blue, C is green. But what I'm going to do is I'm going to draw a dashed line down from the crests and troughs of A. So here we have something like this, this, and this. Well, notice each crest of A lines up with the intercept of C. And then each intercept of A lines up with the crest or trough of C. Just like that. Well, what this tells us is that these waves are definitely out of phase, just by virtue of the fact that the crests and troughs don't line up with each other means that they're out of phase. But how much is this out of phase by? Well, if each crest lines up with the intercept, right? If I wanted this trough here to line up with the trough of the other one, how much would I have to shift it by? Well, that's 1/4 of a wavelength, 1/4 lambda, or 1/4 lambda, 1/4 of a sine wave is 90 degrees, or pi over 2. So that's how much these waves are out of phase by. Okay, so that's it for the video. Like I promised, it's a pretty short one, just about phases and then going back to the properties a little bit. All right.